In this video, we'll discuss the flyweight design pattern, which is another structural design pattern. Now, the flyweight design pattern allows you to set up performance systems which efficiently use resources such as memory. The flyweight pattern is so named because it deals with extremely lightweight objects. A single object might be very small and may not occupy much memory or hog other resources. But when you have thousands of these objects, well, then a little bit of memory doesn't seem so little anymore, and that's when you choose to use the flyweight pattern. The flyweight pattern is a structural design pattern that is used for optimizing code that is slow, repetitive, and shares data inefficiently. These days, where we have powerful machines with a large amount of memory, it's common for developers to not pay attention to the amount of memory that their program uses. However, small chunks of memory inefficiently used and not shared can add up. The flyweight pattern serves to minimize memory use by sharing as much data as possible with related objects. So you have several objects that are similar to one another. There might be some portion of their data that they can share with one another, and that's what the flyweight pattern seeks to do. When you apply the flyweight pattern, you'll examine your objects carefully to see which portion of the data is shared and which portion is specific to that particular object. You'll then extract the shared data from several similar objects and place it into a single external object which all of the other objects can now reference. In the flyweight pattern, you use resource sharing to support a large number of fine grained objects. You'll choose to apply the flyweight pattern when a single object is fairly lightweight. It's not really inefficient to instantiate objects, and when you just look at a single object, it's hard to see how they can be a drain on your memory or any other resource and why a pattern is even needed. But the whole idea of the flyweight pattern is that each object is lightweight, but you have many such objects that you need to create as a part of your code. Each object is small, but managing many of these instances can be inefficient and can be a drain on your resources. Now, you may not realize it, but all high level programming languages, including JavaScript, use the flyweight pattern to store strings. Consider two strings here, ABC and ABC. They're the exact same strings, and both strings are fairly small. Each string has just three characters, and if you consider 1 byte of memory to store one character, then each of these strings just occupy 3 bytes of memory. So each string object is lightweight. The two strings under consideration here have the same state. They are effectively identical strings. There is no difference between the two, no difference in capitalization, nothing. They're the exact same strings. Now, these two strings might be identical, but it's quite easy for you to have two memory locations holding these identical strings, and that is a waste. There is little point in creating two objects and allocating memory for each of these strings separately. They are the exact same string. Why shouldn't you just reference the same memory location where the string is created exactly once? And really, when you think about the number of such strings that you might create when you're writing code, the flyweight pattern starts making sense. So, what you need to do in order to implement the flyweight pattern while using these strings is to use a single object to represent both of these identical strings. You'll share state between objects that are effectively identical. You'll have the strings reside in one memory location, and all variables that reference that string point to the same memory location. Higher level programming languages have been optimized over the course of years, and they all use the flyweight pattern in order to store and reference string objects. Now, the flyweight pattern is very useful when you're working with strings and maybe color values, that is RGB values, red, green, and blue values to represent colors. Now, if you're just going to create a few instances of an object, whether that object is lightweight or not, the flyweight pattern is not really useful. But the flyweight pattern saves precious resources when many thousands of instances need to be created. If you're using the flyweight pattern, you need to watch out though. The semantics of shallow and deep copying can become tricky. Shallow copies essentially reference the same object in memory and then different references can overwrite one another. Now, there are several possible use cases for the flyweight pattern in software programming. For example, if you're writing code that will run on the back end, you'll have to deal with the data layer. You might have to connect directly with databases, you might have to cache data in memory in order to serve that data up quickly. When you're working with the data layer, there is a strong use case for the flyweight pattern to be used. You share data between large numbers of similar objects stored in memory. The flyweight pattern also has special significance when you're working with the DOM hierarchy in JavaScript. The DOM layer sets up a hierarchy of components. You have a tree structure where at the very top of the tree lies the root node of your web page. Every node may or may not contain child elements, and thus nodes are nested one within another. Different nodes in your hierarchy represent different user interface components, and you might want to wire up event handlers to these components. You can apply the flyweight pattern in JavaScript to centralize your event handling. Instead of having multiple event handlers across multiple child elements, you'll have a single event handler at some root node. You'll set up the single event handler to be able to handle all events that occur in the DOM hierarchy. Before we move on to code, let's see a visual representation of how the flyweight pattern can work in practice. So you have a client which basically uses a factory to create many thousands of instances of a flyweight object. The flyweight object is any lightweight object. A single object is a very granular and doesn't take up much memory or any other resource. This factory that we use to create flyweight objects will ensure that all state that can be shared between the different objects are shared. So the flyweight will contain shareable state and other methods that the flyweights may expose. The state that can be shared between the different flyweight objects can be stored in some kind of cache. So all objects have a reference to the same shared state. The same factory will be used to create multiple flyweight objects, maybe even thousands or millions, and all of the objects that can share state will share state. Here is another example of the flyweight pattern in practice. When you use your web browser to browse websites, certain websites may have images. Now, downloading images onto your local machine, that's a fairly heavyweight process and requires additional bandwidth. Images are often far slower to load as compared with text, and this is why the browser is often very smart about loading images. The browser loads images just once and then reuses the images from the pool of images that have been cached on your local machine. So you visited a particular web page and it has four or five different images that have been downloaded and cached on your browser. Let's say you're navigating around on that same website and you move to another page and some of the images are common. The browser will then use the images from your cache rather than downloading them again. This is an example of sharing resources, cached images across web pages. This is an example of the flyweight pattern. If you're working with web pages, a common use of the flyweight pattern is setting up an event handler to handle the different kinds of events that you want wired up to your user interface. If you're building an interactive web page, and I assume that you are, then there'll be a lot of events that you need to wire up to the different components on your web page. Event handlers by themselves might be pretty lightweight, but every event handler that you add takes up resources, and this can really slow down the performance of your page. In this video, we'll discuss the basic idea behind centralized event handling using the flyweight pattern. Now, you might already be aware of how events are propagated in your web page. Now, if you don't really remember and it's been a while, here is a quick primer. Event propagation on a web page occurs in two phases. One of these phases is called event capturing, and this is where an event occurs on a particular element and is then propagated downwards to all child elements of that element. So the original element that received the event gets a chance to react to it, and then the same event is propagated downwards. That is event capturing. There is a second phase of event propagation as well, and that is event bubbling. Event bubbling is when an event is propagated upwards through the DOM hierarchy. There is the original element on which the event was triggered, and once that element has had a chance to react to that event is then propagated upwards to all of the parent elements for that particular event. Now, a DOM hierarchy, where DOM stands for Document Object Model, is, as you know, a top down hierarchy of HTML elements that make up your page. Let's say you have the HTML element that forms the root of this hierarchy. Within the HTML element, as a child, you'll have the body element where the visual content of your web page is embedded. And within the body, you'll have the actual HTML structure of your page. You might have H4 elements, paragraph elements, divs, spans, and image elements. All of these make up your web page, and all of these elements can have their own child elements as well. These elements together make up your document object model hierarchy. This is the HTML of your page, which you'll then style to represent components that users can interact with, which means you might have any of these elements wired up to listen to events. So you can hook up event handlers to elements at different levels in this DOM hierarchy. The DOM hierarchy in real world web pages can be arbitrarily deep. It's not just 10 levels or 20 levels, it can have hundreds of levels, and you can hook up event handlers to elements at any level, at any granularity. And events can be fired by any element within your web page. Events can be keyboard events, mouse events. You might have the user hover over something and something else pops up. So essentially, any element can have an event handler wired to it. Let's go back to our DOM hierarchy here. Elements which are at the very bottom of this hierarchy, which have no child elements, are called the leaf elements. Events can be triggered on these leaf elements as well. Now, other elements might lie in the interior of this DOM. They have parent elements as well as child elements. You may have events triggered by these interior elements as well. Once an event is triggered on an interior element, let's say it is this body tag that you see highlighted on screen here, which other elements receive that event? So once this element has responded to the event, what happens to the event? Do other elements receive it or not? So who should receive events? That is the question. The body element is where the original event is triggered, but which other elements in your DOM page should receive the same event and be given a chance to respond to that event? Now, one way to think about this is that the HTML tag encompasses the body element, so the HTML element should definitely receive all elements triggered by the body element. That seems perfectly reasonable to me, and it does to many others as well. Or another way to think about it is all of these other elements that you see highlighted using the yellow circle, the body element is the parent of all of these elements. The body element encompasses all of its child elements. All of the child elements should also receive the same event. This also seems perfectly reasonable to me. And this brings us to what we had discussed at the very beginning of this video. There are these two ways in which events can travel, and they are called event capturing and event bubbling. So, how does event capturing work? In this DOM hierarchy, let's say you have your paragraph element and that is clicked on. Now, this paragraph will get a chance to react to the event first. This is what receives the event first. Then the event will be propagated downwards to all of the child elements of the paragraph element, and they get a chance to react to this event. When an event is propagated downwards to child elements, that is called event capturing. Let's look at it another way. You click on this paragraph P, and that gets a chance to react to the event first. So it gets the click event first. Then the same event is propagated upwards to all of the parent elements of P. The click is propagated upwards, and this is event bubbling. The term bubbling should clue you in. The event bubbles upwards like bubbles in water. To quickly summarize, let's understand the two ways in which events can travel. Event capturing is where the element first gets a chance to react to the event. With event bubbling as well, the element on which the event occurred, which triggered the original event, gets a chance to react to it first. Then, in the event capturing phase, the click is propagated downwards to child elements and they then get a chance to react to that same event. And in the event bubbling phase, the click is propagated upwards to parent elements and parent elements get a chance to react to that event. So, which one of these phases do browsers actually use? The answer is both. Browsers use both of these methods for event propagation, event capturing, as well as event bubbling. So, for every event that occurs at a particular node or a particular element in your DOM hierarchy, it's propagated upwards as well as downwards. There is actually a little bit of history behind why browsers have now chosen to implement both of these techniques. Originally, different browsers decided on different models for event propagation. So, certain browsers went with event capturing, others went with event bubbling. As you might imagine, this soon got to be very, very confusing. If you were coding up your web page, you had to account for what kind of event propagation mechanism was implemented on the different browsers you wish to support. This is where the DOM Standards Committee stepped in, and the standard that was ultimately adopted was that both should be supported. So, all modern browsers support both event bubbling as well as event capturing phases. Now that you know for sure that all browsers support event bubbling, this leads us to the flyweight pattern for event handlers. The flyweight pattern can be used for centralized event handling in the bubble phase. You can be absolutely sure that no matter on what node in our DOM hierarchy the event originally occurred, it will be propagated upwards. So, what you can do is wire up all event handlers to a single location. And this location should be a root node. So, you could wire up all event handlers to the root node in our DOM hierarchy. So, instead of having a separate click handler for every button on your page, for every tab that you display, for every link that you could have a single click handler wired up to the root node in your DOM. In the bubble phase of event propagation, you know for sure that all of your events will be bubbled up to this root node. At this root node, your click handler only needs to disambiguate the original target of the event and then perform its action accordingly. And this is the flyweight pattern in action. Instead of having multiple event handlers for the different nodes in the DOM hierarchy, that is, many small objects which take up resources, you'll have a single event handler. And in fact, the React library for component driven development uses exactly this approach for centralized event handling. And this is an important reason why the React library is considered so performant. In this demo, we'll see how we can implement the flyweight design pattern in JavaScript. The flyweight design pattern is used with applications that are slow or inefficiently use resources such as memory. In the flyweight pattern, you have multiple granular objects that are instantiated, and you improve the memory footprint of your program by having these granular objects share memory wherever possible. The flyweight pattern thus allows us to minimize resource use in an application by having granular data share memory. Now, what we'll do is we'll see an implementation where we don't use the flyweight pattern. So, the script file where we'll write our code is noflyweightpattern.js. Once we've seen an example of an application which does not share memory for granular objects, we'll improve upon this and implement the flyweight design pattern. Let's imagine you're writing some kind of application that registers students at a university. Now, a student gets scores, and for each range of scores, we have a corresponding grade. We have the class grade defined here to represent the letter grade that a student receives. The constructor for this grade class takes as its input argument the score of the student. And based on the score, We'll assign a letter grade to the student and also a message corresponding to that letter grade. Now, you can perform any kind of range check in order to assign letter grades. Here in this example, if the student's score is greater than equal to 90, the letter grade that we assign is equal to A and the message is excellent. Else, if the score is greater than equal to 75, the letter grade is B and the message says very good. If the score is greater than equal to 60, the letter grade is C, message says not bad. If the score is greater than equal to 40, the letter grade is D and the message says needs a lot of improvement. For all scores under 40, the letter grade is F and the message says not living up to your potential. Now that we've figured out what letter grade corresponds to what score range, we can assign properties for the grade objects that we construct. This dot letter grade is equal to the letter grade calculated. This dot message is the message assigned. And this dot random number we generate using math.random. Now the reason to have this random number is to check whether two objects are exactly the same. The random number here has no real purpose other than to check whether two objects are exactly the same, whether you're reusing objects or creating new objects. There, of course, exists a small chance that two objects end up with the same random number. Since that chance is very small, the probability of that is very low. Let's just ignore that for now and let's move on. I'm now going to define a class that represents a student. The constructor for the class student takes in two input arguments, the name of the student and the score for that particular student. We assign the name to this dot name, the score to this dot score, and we assign a grade to the student by instantiating a new grade object. Now, I'm not sure whether you notice this. Imagine a university where there are thousands of students enrolled. There are just 5 possible grades A, B, C, D, and F. But for each student, we instantiate a new grade object. Where we should have just 5 grade objects, we are going to have thousands. And that is inefficient. That's because we haven't yet used the flyweight design pattern to optimize memory usage, to have grade objects share memory. Let's leave this as is for now and see how this works. Here I'm going to set up two lists, a list of student names and student scores. There are 7 students here in our list of student names and there are 7 scores corresponding to each of these students. I initialize a new JavaScript array called student list, which is currently empty. I'm going to run a little for loop iterating over all of the names of students and their corresponding scores and instantiate student objects to represent each student. Here is our for loop, which iterates from I is equal to 0 so long as I is less than 7, I plus plus, and we'll instantiate a new student object. New student pass in student names of I, student scores of I, and push this student object into the student list. When the student object is instantiated, for each student we would have calculated the letter grade corresponding to the student's score. And the letter grade object would have been stored within the student objects. Let's print out to the console log this list of students and let's examine this. Run this code on the browser. Remember, this is the code where we haven't implemented the flyweight pattern yet. And here is our list of 7 students. We have the student name, the student scores, and a grade object associated with each student. Now, what I'm going to do here is to expand each of the student objects here and take a look at the grade object. Here is a student with grade F. The random number associated with this grade object is 0.395. Let's now move on and take a look at a student with grade A, that is Bella. We can expand the grade object associated with this student. You can see the letter grade is A and the random number starts with 0.222. If you notice, the next student in our list, the student Charles, also has the letter grade A. So I'm going to expand the student object and take a look at the grade object for this student. And you can see that the random number associated with this grade object is different. It starts with 0.743. Both Bella and Charles have the same letter grade, but new grade objects have been constructed for each of these students. This is a major waste of memory and this is a major performance inefficiency. We know that the 2 grade objects are different because the random numbers associated with those grade objects are different. Let's take a look at another student here in our list. This is the student Emily. who has scored just 45 and has the grade D. The random number associated with this grade object starts with 0.745. Keep this in mind while we look at other students that we have here in our list with the same grade D. Here is the student Fiona, her score is 41 and she also has a grade D, but the grade object associated with Fiona has a different random number. This is another instance of the grade object holding the same grade D. This grade object has a random number starting with 0.5677. Let's look at yet another student who has the same letter grade D. This is the student Gerald. Here is yet another grade object that we have instantiated. The random number associated with this object starts with 0.525. If it's just 2 or 3 students that we are dealing with, if we have separate grade objects for them, that's fine. But imagine thousands of students, or maybe hundreds of thousands of students across an entire country. If you had individual grade objects for each of these, well, that's inefficient, and that's what we are going to fix next using the flyweight pattern. From the previous example, it should have been pretty obvious to you that the grade objects need to share memory. For thousands of students, it makes no sense to create thousands of grade objects, even though a single grade object is very lightweight and takes up very little memory. We should share them where possible. We should just have a total of 5 grade objects corresponding to the 5 letter grades. And that's exactly what we'll try and implement using the flyweight design pattern. In the HTML file that corresponds to the flyweight pattern here, I change the script that I'm going to execute. I'll now execute flyweightpattern.js. I'll start writing code on a new file called flyweightpattern.js. I'm going to set up a factory called grade factory, which I'll use to create new grade objects if the grade object corresponding to a particular letter grade does not already exist. If a grade object for a letter grade has been created already, that is, it exists, then it should be reused for other students who have the same grade. Now, within this grade factory, which is an immediately invoked function, I'm going to define the class grade. The constructor for this grade class simply takes in one input argument, that is the letter grade corresponding to this object. Within this constructor, we'll run a simple check to see what this letter grade is and generate a corresponding message for this letter grade. If letter grade is A, the message is excellent. If it's B, the message is very good. For C, we'll say not bad. For D, we'll say needs a lot of improvement. Otherwise, we'll say not living up to your potential. Now that we have the letter grade and the message that goes with that letter grade, let's assign these two properties on the grade object. This dot letter grade is letter grade, this dot message is message, and this dot random number is a number we generate at random. This random number associated with every grade object that we instantiate is what we'll use to verify whether grade objects are being shared across students or whether we are generating a new grade object per student. Now, within this grade factory, I'm going to set up a little object which maps a letter grade to the corresponding grade object. This I store in the variable grade mapping. For every grade object that we instantiate, we'll use this grade mapping to cache that grade object and reuse it as needed. I'm going to return an object from this immediately invoked function, and this object exposes a single function called getGrade. Now, the input argument that we pass into this getGrade function is the score for that particular student, and we'll use the score to calculate what letter grade the student has received. The logic that we've used here is the same logic that we've seen in a previous demo. A score greater than equal to 90 has letter grade A. For scores greater than equal to 75 but less than 90, this letter grade is B, and so on. And for a score less than 40, the letter grade is F. Once we've figured out the letter grade corresponding to the score for a student, we'll check this grade mapping object to see whether a grade object has already been created for this letter grade. If grade mapping does not have a grade object for the letter grade, we'll create a new grade object. The code within the if block here will be executed only if a previous grade object for this letter grade does not exist. If a previous grade object exists, we'll simply return that object. We'll reuse that grade object. We'll return grade mapping in square brackets letter grade. Now that we have implemented the reuse of grade objects, this is our flyweight pattern. Let's write the rest of the code, run this code and see how this works. Here is our class student. To the constructor, we pass in the name of the student and the score for the student. We assign the name and score as properties of the student object, and we use the grade factory to calculate the grade object corresponding to the student. Grade factory.getGrade for this score. I'll now initialize a list of student names and student scores exactly like we did in the previous demo. We have 7 students here and we have 7 scores corresponding to each of these students. I'm going to run a simple for loop to iterate over all of the student names and the student scores, and we'll instantiate student objects that we'll now store in the student list array. For every iteration of the for loop, we'll instantiate a new student object and push it to the end of the student list. Now remember, for every student object we instantiate, it uses the grade factory to get access to a grade object. Now all that's left to do here is to log out this list of student objects and check to see whether the grade objects are being reused like we want them to be. We are now ready to run this code on Chrome and take a look at the array of student objects that have been created. We'll explore these student objects to see whether grade objects have been shared. The first student object that I'm going to expand here is for the student Bella, who has received an A grade. The random number associated with the grade object representing the letter grade A starts with 0.850. Now, let's go ahead and expand another student who has received the letter grade A. This is the student Charles with a score of 91. And you can see the random number here. It also starts with 0.850. In fact, it's the exact same random number, meaning the grade objects are being shared. Our grade factory has created exactly one grade object corresponding to the letter grade A. And this grade object has been successfully shared between the student Bella and the student Charles. Let's confirm the sharing of grade objects by looking at a few other students. We have the student Emily here who has received a letter grade of D. Her score is 45. The random number associated with this grade object starts with 0.1593. Let's expand the information for another student who has also received the letter grade D. This is the student Fiona. The grades are exactly the same for both Emily and Fiona. The grade objects have been shared. The random number associated with both grade objects are exactly the same. They start with 0.1593. And as a final check, let's expand the student Gerald, also with a letter grade of D. And Gerald holds a reference to the same instance of the letter grade D object. We've successfully shared resources across students using the flyweight pattern. Now that you've understood how the flyweight design pattern works and seen how it can be used to have objects share memory and thus be more efficient, let's see another example of the flyweight pattern in action, and this time in the Jquery library. The version of Jquery that we'll use is Jquery 3.4.1, and this is the development JavaScript that I've downloaded onto my local machine and saved in the current working directory. The top level folder is called Jquery Flyweight Pattern. I'll now switch over to the HTML code for this particular demo. In this demo, we'll see how we use the flyweight pattern to optimize event handling. It's often the case when we build up web user interfaces that we have a number of components that are very similar. You might have 4 or 5 buttons which perform similar actions with just a few differences that can be parameterized. Or you might have a number of different tabs, and when you click on a particular tab, you see a different view of your data. Now, one way you can set up event handlers is to have separate event handlers for each of these UI components. But that gets to be pretty heavyweight. What we're looking for is a flyweight solution. Before we take a look at how the flyweight pattern works in jQuery for event handling, we'll look at an example where we have a non optimal setup for our event handlers. We'll have an event handler wired up to each element, even though the different elements have very similar behaviors. The elements that we'll be working with are buttons that we've modeled using divs. Observe that we have a div here with id equal to button container, which is the root div that holds a number of different buttons. The divs nested within the root div are 5 buttons, button 1, 2, 3, 4, and 5. I've applied the same CSS class button to each of these divs. The IDs for these different buttons are different. Button 1, 2, 3, 4, and 5 are the button IDs. And you can see that every button has a message attribute, and the message that the button will display is a little different. Each button displays a different greeting. The first button says hello, the second one says good morning, and the last button says howdy. All of the buttons have different message greetings. Now let's switch over to our JavaScript file and set up event handlers without using the flyweight pattern. This means that we'll wire up a separate event handler to every button in our UI, even though each button behaves in a similar manner when clicked upon. As is usual with all jQuery code that we write, we'll wrap our code within the document.ready handler. When the DOM is ready to be accessed and manipulated, we'll wire up an event handler to every button in our HTML page. Now, this is done because of the selector that we've used. You can see that to the dollar function, we've passed in div.button. This is the jQuery selector that selects all of the divs within our HTML page which have the CSS class button applied. There are 5 such divs, button 1 through button 5, and all of these divs will be selected, and this event handler will be wired up to each of these divs. So we'll have 5 click handlers wired up. We have a click handler on each button, and when you click on a particular button, we show the same alert. The alert says you clicked on this button, and we give you the ID of the button, and we display the greeting associated with each button. The way we do this is by using $this to select the element that has been clicked on, and we display whatever is in the value of the message attribute for that element. And this is a different greeting message for each of the buttons. So we have a separate handler for each button. We haven't used the flyweight pattern yet to centralize event handling in jQuery. Let's switch over to our Chrome browser and click through to jQuery flyweight pattern.html. Here are the 5 buttons that we've rendered in our HTML page. And if you open up Chrome Developer Tools, you'll be able to see the divs that correspond to each of these buttons. I'm going to switch over to the console tab of Chrome Developer Tools, and let's click on a few buttons and see what the result is like. The first thing I'm going to do is click on button 1. Remember, we have a separate event handler for each button, and this button event handler basically executes and displays this alert message. You clicked on this button, button 1. The greeting is hello. Let's head over to another button, let's say button 3, and click on it. And here is the greeting from button 3. How are you? Now you can try this multiple times and each time you'll get an alert message giving you the button ID as well as the greeting associated with that button. Button 5, the greeting is howdy. Our page seems to be working correctly, even though we have a separate event handler for every button. This won't really affect the performance of our code at this scale. We just have 5 different components and 5 different event handlers. Individual event handlers for very similar components become a problem when we wire up many separate event handlers, and we'll proceed to do exactly that. I'm now going to select every button, that is every div which has the button CSS class applied, and wire up a mouse over event. So for 5 buttons, we'll have 5 separate mouse over event handlers that are wired up to our HTML page. And within the mouse over event, we'll simply print out a console log statement. Mouse over on button, and we'll print out the text for that button. The text for any button is simply what is displayed for each of the button divs, which in our case is button 1, 2, 3, 4, or 5. Let's go back to Chrome and hit refresh and see how these multiple event handlers work. This mouse over event handler is something that can be fired very often. Each time our mouse moves over a button, we'll get a console log message, mouse over on button 1. Now we say mouse over on button 2. So as we mouse over on different buttons, we get the console log message because our event handler has been fired. After having moused over a button, you can go ahead and click on it. This will cause the click event to fire. At this point in time, we have 10 different event handlers on our page. 5 click handlers, 5 mouse over handlers. Even with just 5 components, the fact that we have different event handler objects cause these event handlers to add up. And you can see that the actual behavior or the actual code within each event handler is the same. If you want to have a UI that is interactive, you'll probably wire up a number of different event handlers to the same component. For example, in addition to click and mouse over, let's say you have an event handler to handle the mouse out event. Once again, our jQuery selector here chooses all divs which has the button CSS class applied, which means we'll have 5 different mouse out event handlers, one wired up to each div which represents a button. So at this point in time, we have 3 multiplied by 5, 15 event handler objects. Now that we made this change, let's head over to Chrome and see this change in action. We'll hit refresh, and now when you mouse over a button, you get the console message mouse over on button 1. Click will bring up an alert message with the greeting, and when you mouse out, that is your mouse moves out, you get another console message mouse out on button 1. Our page behaves exactly how we want it to. So there is nothing wrong with the correctness of the event handlers that we wired up, but they're not really optimal because we haven't centralized event handling. We are wiring up extra event handler objects when they don't need to be. Now, this problem can be exacerbated when you're working in a UI on the real world. Let's go back to our code here, and I'm going to add in one more event handler to all of the buttons that we display. This is the mouse down event handler. Our jQuery selector here selects all divs with the button CSS class applied. So we'll have 5 different event handler objects, and when mouse down is hit on any button, we'll change the CSS class that we applied to that button so that the button now displays in a different color. Any button on which the mouse down handler has been invoked will be displayed in the color yellow. Background color will be set to yellow. Let's head back to Chrome and hit refresh and see these event handlers in action. At this point in time, we have 20 event handler objects, 4 multiplied by 5. For button 1, mouse over event handler is what is triggered first. When we click on that button, we get the alert message with the greeting. And because mouse down was triggered on the button, you can see that the color of the button has been updated to be yellow. And once our mouse pointer moves out of the button, the mouse out event handler is triggered. You can play around with this page and see how this works. We have 4 different types of event handlers: the click handler, the mouse over, the mouse out, and the mouse down. And for each of the button elements, we have different event handler objects, even though the behavior is exactly the same. And this is what we are going to fix using the flyweight pattern. And that's what we'll do next. We've spoken of the fact that the current code setup that we have isn't really optimal because for each UI component, we wire up separate event handlers and for each event type as well. For 4 different event types, we have wired up 20 different event handler objects, and this is non optimal. We'll now use centralized event handling to improve the performance of our code. Centralized event handling is essentially an implement of the flyweight pattern in a slightly different form and in a different context. What we'll do is have a single event handler wired to the root container for all of our buttons. We have 4 different event types here: click, mouse over, mouse out, and mouse down. So we'll have a single event handler object for each of these event types, and we'll wire up the single event handler for each event type to the root container div that contains all of our buttons. So let's get rid of all of the code that we have here. So I'm going to select all of the event handling code within the document.ready function, and I'm going to add in new event handlers, one event handler to the button container div. Notice the $jQuery selector that we use to select the HTML elements from our page. Hash button dash container is what we have specified in this selector, which means it'll select the div with ID equal to button container. And this is the root div which contains within it all of our button divs. To this root div, we add the click event handler, and this root div will receive click events from all of the nested divs that are its children in the bubble phase of event propagation. Browsers support event traversal through the DOM hierarchy in 2 phases: the capture phase and the bubble phase. The capture phase is when an event is received by a DOM node and then that event traverses down the DOM hierarchy to all of the child nodes or descendants. The bubble phase is when a DOM node receives an event and then that same event traverses up the DOM hierarchy to ancestor nodes or parent nodes. The fact that we have wired up our click event handler to the button container means that we are looking to handle the button click events in the bubble phase. So we'll click on a particular button and that event will be propagated up the DOM hierarchy and the button container will receive that same event and that's where we'll handle it. As an example, let's say the click occurs on button 3. The button 3 div will first get a chance to react to the click event. We have no handler there, and then the click event will be propagated up the DOM hierarchy to the button container div. We do have our event handler here wired up to the button container, and this is what will be invoked. So within the click event handler, we first need to access the original target. This is the actual button that was clicked, not the container element. How do we access this original target? Well, the event handler takes as its input argument the event object that contains the context information and other details. We can run a selection on event.target and that will give us a reference to the original target of the click, the original button that was clicked. Once we have access to the original target element, let's take a look at the class attribute of that element and see if that class name is equal to button. This will allow us to ensure that indeed, yes, it was a button that was clicked and not some other child element. We only want to handle button clicks. We don't want to handle clicks on the button container itself. And that's why this class name check is important. If class name is equal to button, that is, it is indeed a button that was clicked on, we display the alert message that says you clicked on this button. The ID is event.target.id and we get the greeting by getting the message attribute from the original target. And this is all there is to our centralized event handling of the click event for all of the 5 buttons that we have on our HTML page. Hit save on this file and let's head over to Chrome and hit refresh and let's see how this click event handler works. I'm going to click on button 1 and there is the alert. The greeting is hello, the button ID is button 1. The event handler seems to be working fine. Let's click on button 3 and here is the alert from button 3. It says the greeting is how are you? The ID is button 3. Our centralized event handling for the click event works just fine. Our event handler itself was a little more complex, but we have just one event handler object rather than 5 for the 5 different buttons. And this is the flyweight pattern in action. Let's go back to our code and add in another event handler, and this time for the mouse over event. This event handler once again is associated with the single button container div that contains all of our 5 buttons. That is the parent element of all of our 5 buttons. On mouse over, we'll access the original target using $event target. We'll get the class name for the original target and check to see whether this is a button element. If yes, we'll simply print out to the console log that mouse over occurred for this button ID. This is the single event handler handling mouse over events for all of our 5 buttons. The only complexity in this code here is that we have to disambiguate the right button which received the original mouse over event. Let's see this mouse over event in action by heading over to Chrome and hitting refresh. Now I'm going to move my mouse over different buttons and you'll see the console log messages on screen. Mouse over on button 1, mouse over on button 3. As you play around with the web page here, you'll see that we've preserved the original functionality, but this time we've used fewer event handlers because we've applied the flyweight pattern in Jquery. Well, we can never have too much of a good thing, so let's go back to our code here and add in a single centralized event handler for the mouse out event. So this event is wired up to the button container as we did with previous events here for centralized event handling. The code here remains fundamentally the same as the other centralized event handlers. We need to disambiguate the button on which the original mouse out event occurred, and we do that by selecting the event.target, which is the original target, and we print out an appropriate console message. Let's switch over to Chrome and hit refresh and see this mouse out event handler in action. As you move your mouse over the different buttons here, the mouse over event will be fired and then the mouse out event will be fired when you move out of that button. And on a click, you'll see the alert message. Back to our code, there is one last event to wire up here, and that is for the mouse down event. Once again, we'll use the flyweight pattern and set up a centralized event handler on the button container. Within this event handler code, we access the original target, get the CSS class applied, and if it's of type button, we change the CSS for the original target so that its background is yellow. And since we've already discussed earlier how you can play around with this web page, I'll leave you to it. But observe how we brought down the original 20 event handlers to just 4 with centralized event handling using the flyweight pattern. Observe that every button that has been clicked on, that is the mouse down event has been fired, is now yellow in color. The adapter pattern is a structural design pattern that allows your clients to deal with a consistent interface no matter what kind of component they are working with under the hood, whether it's legacy components whose interface might be different, or whether it's newly developed components that have a different and more up to date interface. Now, the adapter pattern, which is what we are going to discuss here in this video, is a structural object pattern. It's not concerned with expressing relationships between objects, but instead it's concerned with object interfaces. How can objects be composed so that it exposes the right interface to the right client? If you only consider the word adapter, what does that mean? An adapter can be thought of as a single class that implements multiple interfaces. And this is the underlying principle behind the adapter pattern. The adapter pattern presents different views of an object in different contexts. Let's say you have an object that can perform multiple actions. There are multiple ways that you can contact a particular user via email, via phone, maybe via a text message. Now, based on your use case, you might want to expose just a subset of these ways to contact the user for different clients. For a particular client, you might want to expose email and phone functionality. For another client, you might want to expose email and text functionality. You can use an adapter to expose the right interface to the right client based on the context. Another very common use case for the adapter pattern is to convert the interface of a class into another interface that clients expect. Now, it's quite possible, as you've been writing code for several years, you have legacy code components around, and your newer clients don't know how to work with these legacy components. But you still want to expose the functionality that these legacy components offer to your new clients. Now, in order to enable your new clients to work with these legacy components, you might set up an adapter. The adapter will convert the legacy interface to the new interface that your clients expect, and this will allow your clients to seamlessly work with legacy components as well as new components. The adapter pattern lets classes work together that could not otherwise because of incompatible interfaces. As its name suggests, the adapter pattern lets you adapt your interface so that previously incompatible services can now talk to one another. Let's see a very simple visualization of how the adapter design pattern might work. Now you have a client, and this client is used to working with the shape interface. And the shape interface has a display method that knows how to render and draw the shape out to screen. Now all of your newer shapes implement this interface and have a display method. But you have a legacy rectangle sitting around from many years ago. At that time, when the legacy rectangle code was written, this is the adaptee, by the way, there was no shape based class, which is why the shape interface did not exist. In order to draw and render this legacy rectangle, you need to use the show method. Now, if you burden your client with this information, if it's a legacy rectangle, then call show, well, that's bad design. What you really need to use is the adapter pattern. You'll set up a very simple adapter class called rectangle, which implements the display function. Now, under the hood, display will simply delegate the displaying of the object to the legacy rectangle. The adapter should perform no heavy duty implementation of its own. It's simply a wrapper around the original legacy rectangle, which is the adaptee class. The sole purpose of the adapter is to enable your client to continue working with the same interface that they are used to, and they can use the legacy rectangle with a familiar interface. Here is the same adapter pattern with a more general example. You have a new application and it's used to this interface, that is the wrapper. This interface has the do this function. But you have some legacy code sitting around. This is your legacy component, which implements the do that function. Now, if you were to expose this legacy component to your new application directly, they wouldn't know when to call do this and when to call do that, which is why you have an adapter. The adapter wraps around the legacy component. The client will invoke do this. Under the hood, this wrapper, that is the adapter, will invoke do that to perform the actual execution using the legacy component. The adapter pattern exists so that your clients need not be burdened with too much knowledge about the different kinds of components that they are working with, whether the components have been developed by different teams, whether they are legacy components, whether they have different interfaces, whether they work in subtly different ways. All of this is abstracted away from clients. Adapters are often used when new components need to work with existing components in a system in a seamless manner. Here is another use case where you might choose to apply the adapter pattern. Let's say you have refactored your code, so now parts of a program uses a new improved interface, but old code which make up other parts of your system still expect the old interface. Now it may not be possible for you to change that as well. Maybe the code is outside your organization, outside your team. Maybe it has to remain a particular way for some other reason. The old code still expects the original interface, so you may use the adapter pattern to expose your new refactored code to the old parts of the system using the original interface. When you code in the real world, your code is often written over a long period of time. So you might have components that you've developed several years ago. Then you've learned new stuff since then, and now you have components which you've developed, say, in the last week or so. It's quite possible that both of these components have similar characteristics, but the interfaces they expose are different. Your old code is important, you don't want to mess with it or change it because it's robust and well tested. It has stood the test of time. And your new code has the right interface, which is more intuitive and developed after a lot of experience. How do you get both of these components to work together? Well, you use the adapter pattern. The adapter pattern converts the interfaces of components to what clients expect. So different classes can then work together in a compatible way when they couldn't previously. In this demo, we'll be using the Jquery library, but the adapter pattern that we'll demonstrate doesn't really have anything specific to do with Jquery. We're just using Jquery to help us build a few boxes. You'll see what I mean in just a bit. Jquery 3.4.1.js is what we reference. Let's head over to adapterpattern.html, and this is what our HTML code looks like. We have a few CSS classes here, and if you scroll down to the bottom, you'll find that the HTML for this page defines 4 different buttons. All of these buttons are held within a top level div called button container. Every div that represents a button has the CSS class button applied, and every div has a box type specification as well. The first button, which says draw legacy box, has box type legacy. Draw orange box, the box type is orange. For draw yellow box, the box type is yellow. And for the draw blue box button, the box type is blue. So these different buttons will draw different kinds of boxes in our code. So let's head over to adapterpattern.js to apply this pattern. As is the case with jQuery, we'll write all of our code within the document ready event handler. Imagine that for several years, the different teams in your organization have been writing code to display boxes onto screen. Now, earlier, for legacy boxes, boxes were rendered using the draw function. So we have the class legacy box, and when you invoke the draw function on this box, it would draw out a box to screen. Within the draw function, we create a paragraph element using jQuery. The text within our paragraph element is this is a legacy box. We add the CSS class box and box legacy, and we append this paragraph element to the div with ID root. So remember, this is a legacy box. This is a component that was developed many years ago with the draw function. That is the API it exposes. But as time has moved on, other teams have developed other components to draw boxes as well. But this time, they've improved the API. They feel the render function is better for drawing boxes rather than the draw function. So we have a team which has developed the class orange box. And the orange box class has a render function, which is what we call to render or draw this box out to screen. The box itself is a paragraph HTML element. The text within this box says this is an orange box. We add the box and box orange CSS classes and append this box to the div with ID root. Yet another team has developed the yellow box component, and they've also chosen to use the new API. The yellow box has a render function within it where we set up a paragraph element which says this is a yellow box. We add the CSS classes box and box yellow and append to the div with ID root. And finally, there is yet another team which has developed a component to draw a blue box to screen. The team which developed the blue box component also chose to use the render function because they felt that was more intuitive. So we have one legacy component and three components that implement the new API. All of these box renderers we expose to other teams which might need to draw boxes. So here I have a variable called box renderers, which is just a dictionary object or a JSON object where we have the different types of boxes set up in the form of key value pairs. The keys here give us the name of the box: legacy, orange, yellow, and blue, and the values are an instance of the box object. Now, a team that wants to use these box renderers to render out boxes might write an event handler that looks like this. So, I have a number of buttons displayed on my HTML page. I wire up a click handler to each of these buttons. I'm not really using the flyweight pattern here because we are focused on the adapter pattern. Any client which wishes to be able to draw all of these different types of boxes now needs to know whether it's a legacy box or a box component that follows the new API. So, does the client need to call draw or render? Well, the client needs to explicitly perform a check before it invokes the right function. Here in this event handler, we access the button that was actually clicked on and get the value of the attribute box type. We then check to see if the box type is a legacy box. If yes, then we use the box type to look up the box object within box renderers, and then we need to invoke the dot draw function on the legacy box because remember, the legacy boxes implemented the draw function, not the render function. Now, this might not seem like a big deal here, but if you have multiple legacy components and other components that follow the new user interfaces and you have many clients using this, well, this can be pretty painful. For all other box types that implement the new API, we need to look up that particular box object in the box renderers and invoke the render function because the render function is the new API. Well, this is painful, but it'll work. Let's switch over to adapterpattern.html, click through, and let's draw a bunch of different boxes. I'm going to open up Chrome Developer Tools here, and here are all of these buttons that I'm going to click on in order to create new boxes. This web page will work perfectly correctly, but the code is implemented without using the adapter pattern. So if you click on draw legacy box, a legacy box is drawn. And if you expand the div with ID equal to root, you can see the paragraph element that makes up this legacy box. And it says this is a legacy box. Let's go ahead and click on all of the other buttons here to make sure that our event handlers have been wired up right and the right APIs are being called on the different components, the legacy components as well as the new components. Observe that for every click on any of these buttons, a new paragraph element is appended to the div with ID root as a child of the div with ID root. So here are all of the boxes that we've generated, but we haven't used the adapter pattern. So far, we've been drawing legacy boxes as well as boxes which implement the new API without using an adapter. Now, this is not really a great way to set up code. Now, for this very small program, it may not seem like a huge burden, but what we've done is pass the responsibility onto the client for figuring out whether a component is a legacy component or a component that implements the new API. This responsibility or burden should not lie with the client code. Instead, it's up to us to provide a uniform interface to our clients, and that's exactly what we'll do next. This time, we'll use the adapter pattern to make sure that legacy components also expose the new API. I'm going to get rid of some of the code that I'd written before, all of the box renderers and our button event handler, and I'll replace it with code that will use the adapter pattern. The objective of the adapter pattern is to ensure that our legacy components expose the same user interface as our new components. And to accomplish this, we'll set up a class that is the legacy box adapter. The constructor for this class takes in an instance of a legacy box and assigns it to the property this.legacyBox. So this legacy box adapter wraps a legacy component. So this legacy box adapter knows that legacy components have to be drawn using the draw API. This legacy box adapter also knows that new components expose the render API for drawing. So this legacy box adapter uses the new API, exposes a render function to all users of this legacy box adapter, but inside the render function, it'll invoke this.legacybox.draw. So it's essentially adapting the render function to call the draw function under the hood. Now that we have this adapter class, we can now set up our box renderers as we did before. This is a JSON object that is key value pairs, and for each key, we have a box object. The one difference here is that for the legacy box, we instantiate a new legacy box object and pass that into a legacy box adapter. So the actual object that is a box renderer will be the adapter object. So our clients will never work with the legacy box directly. They'll always work with the legacy box adapter. And what this means is that our client code now will be very simple. Here is the event handler to draw box. We select all of the divs with the button class applied, that is all of the buttons in our HTML page. We extract the value for the box type attribute, and no matter what box type it is, we simply invoke box renderers, look up the particular box using the box type, and use the dot render function to draw the box. The legacy box adapter and all of the new box components have the same function. So our client code now becomes very simple. Save this change and let's switch over to the Chrome browser, hit refresh, and you can now click through all of the boxes and ensure that this web page functions as you would expect it to. I'm first going to click on the button that says Draw Legacy Box because I want to make sure that my adapter is working fine. Click on that and you can see a legacy box is displayed on screen. And if you expand the div with ID equal to root, you can see the legacy box paragraph element. Now let's go ahead and click on all of the other buttons and you'll see that the different kinds of boxes will be drawn on screen. Everything works as expected. We've used our adapter and made the client code simple. In this video, we'll discuss the composite design pattern. The composite design pattern allows us to treat individual objects and aggregations or collections of objects in exactly the same manner, thus abstracting away from clients the complexity of knowing whether they're dealing with one object or several objects. The basic idea behind the composite pattern is that of a composite. A composite describes a group of objects that can be treated the same way as a single instance of an object may be. The most natural way to represent composites is in the form of a tree structure. A tree structure contains a root node and then nodes which are child elements of the root node. So you'll compose objects into these tree structures, and a particular node might be an interior node or a leaf node. When you write algorithms that work with trees, you don't actually differentiate between nodes that are interior nodes or leaf nodes. You treat all nodes in exactly the same way. But these two kinds of nodes are actually different. An interior node represents a collection. All of the child nodes which are descended from that interior node make up the collection for that interior node. On the other hand, a leaf node is a single node or an individual instance. If you're designing your algorithm such that it works correctly on tree based structures, what you're implementing is the composite pattern. You're treating interior nodes and leaf nodes in exactly the same way. You're treating individual instances and collections in the same way. The composite pattern is extremely useful when an application needs to manipulate a hierarchical collection of objects. And the moment I make this statement, it should become immediately obvious to you why this pattern is so important in the world of JavaScript and web pages. Whenever we are working with web pages, we are dealing with a DOM hierarchy, and a DOM hierarchy is a tree based hierarchical structure. The objects that you deal with in a composite pattern can be a single instance, those are primitive objects or collections of these objects. The idea behind the composite pattern is that you should be able to treat single objects and collections in exactly the same manner without having the client know the difference. Now, if you did not implement the composite pattern, you're actually burdening the client because the handling for primitive objects, that is, individual instances, is typically different than how you would handle collections of these objects. The interfaces might be different, the methods exposed might be different, the operations that you perform might be different. If you expose these differences to clients, the clients would have to check before they perform an operation whether this is a single instance or a collection of instances, and that can get quickly cumbersome. And that's why you need the composite pattern to avoid type checking before performing operations. This makes coding for your clients less cumbersome, less prone to error. It's just easier and more intuitive to not have to think of single objects versus collections. If you implement the composite pattern, every object, whether it's a single object or a collection, is thought of as a composite, and the composite can be treated atomically just like a single instance or a leaf node. You'll then just invoke the right methods to perform operations on this composite without knowing how many objects exist, how many objects will be affected due to your operation. You don't care whether it's a single object, two objects, three, or 100. A classic example of a composite in the real world is a directory on your local machine. Directories contain files. Files can be thought of as leaf nodes or leaf elements in this tree structure. Directories contain within them other directories, and these other directories may contain files and directories further composed within them. Let's imagine the tree based structure that is used to represent a composite in a visual manner. Here we have a hierarchy of components, and you can see that every interior node here is a composite. It represents a collection of elements. Every node that is marked as a leaf is an individual instance. The composer should set it up such that whatever operation you choose to perform should be performed in the same way for composite nodes as well as leaf nodes. Let's consider this composite here, which is an interior node. An operation on a composite should recursively perform the same operation on all of the nodes or objects which are part of this composites collection. The composites collection include all of the leaf nodes which are contained within the composite, and there may be multiple levels of nodes here. That same operation, were you to perform it on a leaf node, will be applied only to that leaf node on no other nodes. The clients need not know the difference. All the clients need worry about is that they invoke the right method to perform the operation that they want to execute. Whether it's performed on one node or multiple nodes, well, it doesn't matter. When you implement the composite pattern, you need to expose an interface that clients have access to, which they can use to perform their operations. Let's say this is the interface component that you expose, and you have exposed the method do this, which performs some kind of operation on the composite. This same interface is implemented by leaf nodes, which are single instances or a single object. The leaf node has an implementation for this do this method that you've exposed. We have a composite as well, which represents a collection of elements, a collection of individual instances. The composite may have other methods that it exposes, maybe a method to add elements or remove elements from the collection, but it implements the same interface, do this, where the action or operation is performed on all elements of the collection. All the client is aware of is this single interface component with the method do this. The client can peacefully invoke this do this functionality, whether it's a leaf node or a composite which contains a collection of elements. In this demo, we'll see an example of the composite pattern in action in jQuery. Now, selectors in jQuery is something that we've been using for a while now across many demos in this course. We've seen that selectors in jQuery can be used to select either a single object or a collection of objects, and then we perform actions either on a single object or on a collection in exactly the same way. This is exactly the composite pattern. The whole idea behind the composite pattern is that it allows your clients to treat individual objects, that is, a single object, and a collection in the same way. You have certain actions that you want performed, and these actions can be performed on a single primitive object or a collection of primitive objects. The API exposed should be exactly the same, and your client should not know the difference. And that's exactly what jQuery offers, and we'll explore this. We'll be using jQuery selectors of different types in this demo, and we'll have our web page be a little interesting. It'll have a bunch of different images embedded. It'll have an image of a bird, three dogs, and four images of nature. Now you can click through and explore these images here within your Sublime Text editor, or you can view them directly on your web page. What's interesting here is the composite pattern as implemented in jQuery, and for this, let's start first by exploring the composite pattern.html file. This file has a bunch of CSS classes that I've defined. These are relatively simple and easy for you to follow. Let's scroll down below and take a look at the HTML. Our web page here displays four buttons, each button with a different ID. We have the toggle all button with ID equal to all, toggle bird button ID is equal to bird, toggle dogs with ID is equal to dogs, and toggle nature with ID is equal to nature. In addition to these buttons, we then have a bunch of divs and image tags which display the different images onto our web page. An image of a bird, three images of dogs, and four images of nature. We can now head over to compositepattern.js and take a look at how the composite pattern allows us to select either single or multiple objects in jQuery. As usual, we'll write all of our jQuery code within the document ready function. In just this little bit of code, you'll see the composite pattern in action for two primitive objects. First is our selection of the div to which we want to wire up this event handler. This is the div with ID equal to bird. So we use the dollar selector and specify hash bird, indicating that we want to select the one element that has ID equal to bird. This is a single button. Now that we've seen how we can select a single primitive object, that is a single HTML tag, let's take a look at the contents of the event handler. When we click on this button, we'll show and hide the bird image using the slide toggle function. Now, in order to apply the slide toggle animation, we'll need to select the elements that we want animated. And once again, we use the dollar selector and specify hash bird dash image. And because the hash represents an HTML tag with a specific ID, exactly one HTML tag will be selected. Remember, IDs for HTML tags on your web page are unique. The jQuery selector here will just select that single div with ID equal to bird image and apply the slide toggle animation there. Now let's see how this works. Let's switch over to our Chrome browser and click through to compositepattern.html, and here is what our web page looks like. We have all these images displayed of a bird, three dogs, and four images of nature, and we have four buttons that will perform animations on these images to show and hide these images. Let's take a look at the HTML structure of this page. Here are the divs representing the four buttons, and here below are the divs that hold the different containers. The div that contains the image of that little chick has ID equal to bird image. That's the only HTML tag with that ID. Now you can expand the other bits of HTML here. I'm now going to expand all of the HTML here in this page so you can see exactly what's going on. You can use it to explore what the page looks like. But what I'm really interested in is clicking on the toggle bird button which will apply the slide toggle animation on my bird image to show and hide the bird image. I click on toggle bird and my bird image is now hidden. If you click on toggle bird once again, the image will be displayed. This is the slide toggle image, which is now applied just to the single selected element. You can try this out a bunch of times and see how the selector works when it selects just a single HTML element. None of the other events have been wired up yet. None of the other buttons work. Let's fix that. On my code editor, I'm first going to select the button with ID equal to dogs. This will just select the one button element, the one div, and I'm going to add a click handler to it. Within this click handler is where you'll see the composite pattern in action. The dollar selector that I've used will select all of the elements that has the dog CSS class applied. Now this could be a single element or multiple elements, it does not matter. You invoke the slide toggle function on all of these elements in exactly the same way. This is the composite pattern. Now it so happens that on our HTML page there are three divs which have the CSS class dog applied. You can see that for all three dog images, the outer div has classes equal to inline as well as dog, which means this particular selector will select this collection of three elements. Observe that we invoke the slide toggle function in exactly the same way as we did when a single element was selected. Back to Chrome to see how the selection of multiple elements works with the composite pattern. In order to help you see exactly what's going on with the HTML of our page as we perform the toggle, I'm going to expand all of the elements. Go ahead and click on toggle dogs. It's wired up now. And the slide toggle animation hides all of the dog images. If you click on toggle dogs again, the images all come back. We're applying the slide toggle animation on three images at a time using the same method invocation that we used for a single image where we toggled the single bird. So you can try toggling the bird. It works the same way as the slide toggle for toggle dogs. Let's head back to our code here and we'll wire up yet another event handler. This is a click event handler on the button with ID equal to nature. Within the click event handler, we use the dollar selector to select all elements on our page which have the CSS class nature applied. Now it so happens that there are four such elements on our page, the four divs that contain within them images of nature. All four of these will be selected and the slide toggle animation will be applied to them to show and hide these images. Let's take a look at this going back to Chrome. Hit refresh in order to see the new event handler in action. I'm going to expand all of the HTML of this page so you can see exactly what's going on when I click on the toggle nature button. Click on this button and here is the slide toggle which hides all four of the nature images. Click on the button again to display these images once more. Observe how single selection as well as multiple selection use the same APIs. Try toggling dogs, try toggling the bird. The composite pattern makes working with single elements and multiple elements seamless. One last demonstration of the composite pattern in action using jQuery selectors. I'm going to wire up the button with the all ID to a click handler, and this click handler will select all of the images on my web page using the image tag selector. I've specified the img_html tag as a selector within my dollar, and this will select all of the images that I've displayed. The one bird image, the three dog images, and the four nature images. The structure of our event handlers were more or less the same. This time, we'll see how the toggle all works, which selects all of the images on my web page. I'm going to expand the entire HTML structure within Chrome Developer Tools, and let's head over to the toggle all button and click it. And once you click it, you'll see the slide toggle animation is applied to all of our images, and all of our images are now hidden. If you click on toggle all once again, the slide toggle animation will be applied and all of our images will be displayed. In this video, we'll move on to discussing another structural design pattern. This is the proxy pattern. Now, a proxy is something that you might have encountered if you've been programming even for a little bit, because the proxy design pattern is widely used in practice. So, what exactly is a proxy? A proxy is a surrogate or a placeholder for an object in order to be able to control access to that object. What you're trying to achieve with the proxy design pattern is to not have your clients use an object or a resource directly. Instead, all of their access is directed or gated through a proxy object. The proxy object typically has the same interface as the actual resource or the object that it is the proxy or surrogate for. Under the hood, all invocations that you make on the proxy object are redirected to the real resource. The proxy object does not contain any implementation. All of the implementation is in the real resource. The proxy object is extremely useful because it offers an extra level of indirection to support distributed, controlled, or intelligent access to the resource. For example, under the hood, let's say you're working with a cluster of machines and you want to run processes on this cluster. Now, instead of interacting directly with the cluster as a whole, you might interact with a proxy for that cluster, which may be the master node of the cluster. A proxy can also be used to control access, maybe perform authentication checks to make sure that you're authenticated and authorized to access that particular resource. Now, there are several cases where you might want to use the proxy design pattern. When you want a wrapper to protect the client or the user of your resource from undue complexity. So you'll hide all of the complexity behind the proxy. The proxy kind of acts as a facade. Now, when you're writing code, if you're working with networking applications, you'll find that the proxy design pattern is extremely common. You might use a proxy in order to make remote procedure calls, calls that access another machine or another computer. You might want to use the proxy pattern for lazy instantiation of a resource as well. The proxy pattern can provide other useful functionality. Let's say you have a complex object that is hard to create and takes up many resources. You don't want to instantiate this object unless absolutely needed, only if the rest of your application code references this object. If you hide this object behind a proxy, you can use the proxy for lazy instantiation for hard to create objects. Let's see a visualization of how the proxy pattern might work. You have a client, and this client interacts with an interface that you've exposed from your service or component. This interface is the subject, and the interface has this method called do something. Now, this is just the interface. The implementation is actually not directly exposed to the client. It's possible that this interface, the subject, talks to a proxy behind the scenes. The proxy is the wrapped object. The interface has a reference to this proxy. It will then invoke the do something function on this proxy. Now, the proxy behind the scenes will talk to the real subject. Before the client talks to the real subject, there is all of these levels of indirection where you can add in additional checks. You can check whether the client is authenticated and authorized to access the real subject. The proxy will take care of wrapping up all of the input parameters that you've specified, and then it will invoke the do something function on the real subject. The real subject contains the code that performs the actual operation. And once the operation has been performed and the results have been received, these results are then passed back to the proxy. The proxy will then pass this information on to the interface, and from the interface, it will move on to the client, and the client will receive the results that the client wanted or was looking for. In the real world, you often have proxies for payment systems. The actual payment is made from your bank account, but you may not interface with the bank account directly to make a payment. You might use a credit card or debit card to make a payment. The funds will ultimately be paid out from your account. That is the real subject. The same bank account might have different proxies. Credit and debit cards are examples of proxies. You might have a mobile app that deducts funds directly from your bank account as well. Another example of a proxy for your bank account that you see visualized here in this diagram is that of a check. You write out a check to somebody. The check is a proxy for the funds that exist in your bank account and ultimately will be paid from your bank account. So, how would you make the decision as to when to use the proxy pattern? Here are some standard use cases. You need to control access to a specific object using authentication. The real subject might be something like a database. You need to specify a username and password that is valid before you can connect to that database. The proxy might check the username and password that you have provided against the database system, see whether this is valid, see whether you have access, and only provide access if everything matches up. Another example of where you might choose to use the proxy pattern is to cache heavy duty requests. And this is an example we'll see in the demos that follow. You make requests to the server in order to retrieve data, but you may not want to go back to the server again and again for data that is commonly used. If you can cache it, you'll cache it using a caching proxy and you'll serve the data from cache next time your application makes the same request. You'll only make the round trip to the server when the data is not available in the cache. Another situation where you might choose to use a proxy is to mask the complexity for distributed access. Let's say your database is not on a single machine, but it's a distributed database across a cluster of machines. Now, you don't want to expose this complexity to your clients, so you'll have all of the client requests flow through a proxy which will take care of sending the request to the right node in the cluster. Thus, using the proxy pattern, the distributed nature of your database processing is completely masked from your. In this demo, we'll see an example of the proxy pattern in action. The proxy, as you know, is a surrogate or a placeholder for another object, and the proxy is often used to control access to the other object. Other uses for the proxy are to cache data, provide intelligent access, abstract away the distributed nature of computing, and so on. We'll be using the Jquery library once again for this demo, but the proxy pattern that we'll implement does not really depend on Jquery. We'll use Jquery to make AJAX requests to our fake REST API server. Let's head over to proxypattern.html. There are a few CSS classes here that I have defined just to style my elements. What's interesting here is the HTML structure of the page. I've set up 4 different buttons here, which makes a request for 4 different posts from our fake API server. The first button, called post 1, has post ID set to 1. The second button is post 2, post ID is 2. The third button, post 3, has post ID 3, and the fourth button, post 4, has post ID 4. Post ID is the attribute that we'll use to reference the ID of the post that we want to retrieve from our REST API server. Let's head over to proxypattern.js and see how we can use this proxy to cache data that has already been retrieved from our server. As usual, we'll be writing all of our jQuery code within the document ready function handler. Let's set up the class for our proxy. I've called this class post data proxy. This proxy is so called because we use this to retrieve user posts from our server. The post here refers to user posts and not the HTTP post request. In order to retrieve these posts, we'll be making HTTP GET request. Let's take a look at the constructor of this post data proxy. We instantiate an object this.postData to be the empty object. This is where we'll cache the content that we'll retrieve from the server, and we'll return cached content where possible. Within this proxy, I'm going to have a method named displayPost, which takes as an input argument the ID of the post that we want to display. In order to display the post with this specific ID, we'll first check our cached content. We'll check to see whether we've previously retrieved the post with this ID. If this post data ID does not exist, that means the data hasn't been cached. We haven't made this request before. We need to make a request to the server. So if cache data isn't present, we'll print out to the console log making server request for and specify the ID, and then invoke the function this.loadPost and pass the ID in. The else block here handles the case where we've previously retrieved the contents for the post with this specific ID, and these contents are available in our cache. So if the contents are available in our cache, we'll print out to the console log cache data already available for this ID, and then invoke the this.display function and pass in the cached post with that ID. When cached data is available, this proxy will display the post directly instead of retrieving the data from the server. So it's a caching proxy. Let's go ahead and write the code for the load post function. This method is invoked only when the cached data for a particular ID is not present within this proxy. So load post takes as an input argument the ID and makes an AJAX get request to JSON placeholder.typicode.com/posts. This get request will retrieve the post with the specific ID, and when we get a successful response from the server, we'll invoke the function this.cache post data. And when we invoke this function, we'll bind it to the current instance of this object. We'll call dot bind this. This leads us straight to the code for the cache post data function, which takes as an input argument the response that we receive from the JSON placeholder.typicode.com server. The response contains the post response, and we'll simply cache the content in the this.postData object. The post with the specified ID available in response.id is now part of our cache. And now that we have it as a part of our cache, we can invoke this.display to display the contents of this post. The only function that we yet have to write code for is the display function. The display function takes as an input argument the contents of the post that have to be displayed onto our web page. We'll keep this very simple. We'll select the div with ID root. We'll convert the post data to the string format using json.stringify and display it as a part of the text of that div. We'll also style this with the CSS class box. This post data proxy that we've set up is a caching proxy for server requests. It controls access to HTTP requests that we make to a server and caches whatever data we've retrieved from the server. So we don't make server requests unless absolutely necessary. Go ahead and instantiate a new object for this proxy, new post data proxy. I'm going to wire up an event handler on every button on this web page, and whenever a button is clicked, we'll extract the value for the attribute post ID from that button. That is the ID of the post that we'll retrieve from our API server. Once we know the ID of the post that we want to retrieve, we'll use our post data proxy and invoke the display post method on it and pass in the post ID. The proxy will take care of everything else. It'll make an HTTP GET request if the cache data is not available on the client. Otherwise, it'll simply display the cached client data. Let's head back to Chrome and click through to proxypattern.html and see our caching proxy in action. Here are our 4 buttons to retrieve posts with ID 1, 2, 3, and 4. Let's play around with this page and see how it works. I've expanded the HTML structure of this page so you can see exactly what's going on. I'm going to click on post 1, and you can see that post 1 has been retrieved and displayed on our web page. The div with ID equal to root contains the contents of this post. Now, how do we know whether a server request was made or not? One way we can figure this out is by heading over to the console tab of Chrome Developer Tools, and we can see the console log message here which says making server request for 1. Clicking on any of these buttons invokes the display post function on the post data proxy. Now, if the data is not cached, we make a request to the server by invoking this.loadPost, and we print out to the console log indicating that we are making a server request and the data is not in cache. I'll click on another button here, that is the post to button, to retrieve the post with ID 2. When I click on this button, you can see that we make a server request for 2 because the post data is not cached on our client. We haven't previously requested for this data from the server, so it's not available on our local browser. Now let's go ahead and click on the post 3 button here. And once again, since the data is not available on the client, we'll have to make a request to the server for post with ID 3, and then it's retrieved from the server and displayed on our screen. I'm now going to click on the button to retrieve post with ID 1. Remember, this is a post that we've previously requested from the server. It's now available on our local browser. We have cached it within our proxy, and that's where it's served from. It's served from our cache. The contents of post 1 are displayed within my box, but we haven't retrieved these contents from the server. We've retrieved them from the cache. Cache data already available for 1. That is the message that we have within the console log. I'm now going to try and click on post 2. This is also a post that we've retrieved earlier. Once again, the data is from cache. Cache data is already available for 2. Now, if you click on post 4, remember we haven't previously retrieved 4, which means our proxy will make a server request for 4. But let's say you were to click on the button post 3, which retrieves the post with ID 3. Well, that's already available on our cache and will be served from cache. Let's head over to the network tab here to take a look at what requests have been made to the server. You'll see that exactly one request was made for post ID 1, one for 2, one for 3, and one for 4. We did not make multiple requests for a post with a particular ID. Once the data was available in cache, it was served from cache. I'm going to hit refresh and start again, but this time we'll keep the network tab open. So far, we've made no HTTP request to get post data. I'm going to go ahead and click on post 1. This data is not available in cache, and that's why you can see a server request was made with ID 1. Now, if I were to go ahead and click on the post do button to retrieve the post with ID 2, this also needs a server request, and you can see this on the network tab as well. Let's click on post 3, and a third server request is made. All of this data is not available in the cache. I'm going to go ahead and click on post 4 as well so that we have all of the post data now available in our cache. Now go back to one of the other buttons. Let's say it's post 1 and click on it. But this time, even after you've clicked post 1, the contents of your display box have been updated, but no additional server request has been made. And you can take a look at this within your console messages. Cache data is already available for the post with ID 1, and that's what is retrieved. Another application of the proxy pattern, one we haven't explicitly discussed so far, is to have the proxy control the context for a particular function or an object. Now, it's often the case in the real world that when you write code for a particular function, you want to ensure that that code is executed in a surrounding context. The context makes sure that environment variables and other initialization is set up correctly for that function to execute. The proxy pattern can be used to provide the right context for this function to ensure that this function always executes within the context that you've specified. And in this demo, we are going to use the Jquery library, which has a built-in method called the proxy method, which can be used to provide the right context for a function to execute. Let's switch over to our Jqueryproxypattern.html page. It has some CSS classes which are relatively straightforward, and if you scroll down to the bottom, there are a few HTML elements here as well, specifically two divs representing buttons. The first button says bigger and its ID is equal to bigger. The second button says smaller and its ID is equal to smaller. And below that, we have another div which represents a box. It is this box that the buttons will make bigger and smaller using jQuery libraries. And we'll have the event handlers that we wire up to these buttons operate in the right context using the proxy pattern. Let's switch over to jQueryproxypattern.js where we'll write our code. As usual, our jQuery code will be within the document ready event handler. First, we won't be explicitly using the proxy pattern, and you'll find that jQuery applies the proxy pattern implicitly. We'll see how. Take a look at this event handler that we have wired up to the two buttons that we have on our HTML page. We've used the jQuery $selector to select all divs that have the button CSS class applied. There are exactly two of them. And we wired up a click event handler to each of these buttons. The event handler is a function which takes as an input argument the event object. And the event object is what jQuery uses to pass additional information to the event handler, which can be used to handle the event. Now, what jQuery does automatically behind the scenes when this event handler runs is to automatically bind the target of this event, that is, the object on which this click event was fired, to the this reference within the event handler. So, if you want to access the ID attribute of the target of this event, you'll simply select $this, then you'll invoke the attribute function and extract the value of the ID. When you use jQuery event handling, referencing this from within the event handler will automatically give you access to the object on which the event was fired. This binding is done for you by jQuery, and jQuery ensures that the context of the clicked on object is always available within a jQuery event handler. After extracting the value of the ID attribute on the event target, let's print out to the console log the value of this. You'll see that this is the object on which the event was fired. Now, if the ID is equal to bigger, that is, the user clicked on the bigger button, let's select the box div and animate it so that it becomes larger in size. We'll increase its height and width by 50 pixels. In order to do this, we'll use the .animate function provided on a jQuery element, and we'll specify height and width plus equal to 50 pixels. This is if ID is equal to bigger. If the ID of the button that was clicked on is equal to smaller, we'll animate the box once again, but we'll reduce the height and width of the box by 50 pixels. Height and width will be minus equal to 50 pixels. So far, we haven't used the proxy pattern within this event handler because it wasn't needed. The context in which the event handler executes is automatically set up correctly by jQuery itself. Before we see when the proxy pattern is needed, let's switch over to Chrome, click through to jQueryproxypattern.html and see how this works. I'm going to open up Chrome Developer Tools, and let's keep the HTML structure of this page open and click on the bigger button. Once you click on bigger, notice that the size of the box displayed on screen was immediately incremented by 50 pixels along the height as well as the width. The height and width of the box is currently 150 pixels. Now let's switch over to the console logs, and you can see the value of this within the event handler. We had clicked on the bigger button, and the value of this within the event handler is the HTML div for this button. Let's go ahead and click on bigger a number of times, and each time our box size increases by 50 pixels in each dimension, and the value of this within our event handler is always the button on which we are performing the operation. Let's try this again by clicking on the smaller button. This time, the animation is applied on the box to make its size smaller by 50 pixels. For every click on the smaller button, we can switch over to the HTML structure of this page and observe how it becomes smaller by 50 pixels on each dimension when you click on the smaller button. Now you can play around with this page, but we haven't really implemented the proxy pattern yet, and that's what I'll do next. So let's head back to our code. So far, our event handler has executed within the right context, and we haven't needed to use the proxy pattern. But this can change under certain conditions. In order to see when, I'm going to comment out all of the code that we have right now. Our event handler has worked perfectly well so far, but what if I wanted my event handler to have a slightly different behavior? Instead of animating the box to be bigger and smaller right away, what if I wanted a gap of about 2 seconds after the button was clicked and then run the animation? Well, it's easy to do that using the set timeout function. Once again, I wire up click event handlers to both of the buttons that I have on the web page, the bigger as well as the smaller button. But now this time, I don't want the event handler code to run immediately, so I invoke the set timeout function within my JavaScript web browser. Set timeout takes as an input argument the function that you want executed after a certain timeout, and the timeout that I've specified here is 2000 milliseconds, that is the same as 2 seconds. So the animation code to make our box bigger and smaller will run after a gap of 2 seconds. The function that we pass into set timeout will execute the same event handling code as we had before. We'll extract the value of the ID attribute using the this reference. And you'll see here is where issues will arise. When you pass in a function to the set timeout function, you'll need to specify the context for this particular function that will be executed after 2 seconds. The value of this is not set automatically, and we'll see this by printing out the value of this to the console log. This function runs after a specified timeout, and because we haven't explicitly bound the this reference, this will refer to the window object of our browser. It will not refer to the object that fired the event. And in a sense, what will happen that the rest of the code that we have here, where we check whether the ID is equal to bigger or smaller and then animate our box accordingly, will not work. The ID will never be equal to bigger or smaller because we haven't used the right this reference to extract this ID value. We'll end up in the else block where we have the console log statement invalid ID and we'll print out the current value of ID. Before we see this in action, I should tell you upfront that this will not work because the function does not execute with the right context. It does not have the right reference to this. I'll head over to the Chrome browser and hit refresh. And this time, when we click on the bigger button, let's see what happens. I'm going to click on bigger and nothing happened. The box didn't really get bigger. Let's take a look at the console logs here. Take a look at the value of this. We can see that this refers to the window of the browser. When our function code executes on a timeout, the this reference is not bound automatically to that function. We have to explicitly bind a reference to this. You can see that the ID received was undefined because obviously the window object within our browser does not have the value that we expect for the ID attribute. You can try this a number of times. Click on bigger, and each time the value of this is set to the window object. And the same thing is true when you click on the smaller button because this event handler is not running with the right context. It doesn't work as we expect. Now that we've seen the issues that can arise, let's head back to our code and use the proxy pattern in jQuery to provide the right context for our event handler. I'm going to comment out all of the code that we have so far and write some code afresh. Once again, I wire up the click event handler to the two buttons that we have on this page, and our objective remains the same. I want the button handler to animate the box to be 50 pixels bigger or smaller, but I want to do this on a timeout. Within our event handler, we'll use the set timeout function to execute the behavior of this event handler. But this time, we'll ensure that the function executes with the right context. We'll bind the function to the this object. Remember that this within the event handler references the object on which the event was fired, and that's what we're binding this function to. The only difference here from the previous implementation is that we have the additional bit of code dot bind this, which binds the execution of the function to the this object, that is the event object on which the click event was fired. This will now be the context in which this function is executed. This is one way to apply the proxy pattern in jQuery without the use of the proxy method, which we'll see next in just a bit. Let's set up the rest of this event handler. The first thing I'm going to do is to print out to the console log the value of this. I want to make sure that the this reference within this function has the right value. This function executes within the right context. The rest of the code here is going to be exactly the same. If ID is equal to bigger, we'll animate the box to be 50 pixels bigger in each dimension. If ID is equal to smaller, we'll animate it to be 50 pixels smaller along the height and the width. And if the value of the ID attribute extracted is invalid, we'll print out to the console log invalid ID. Let's head back to Chrome and run this code of ours, which implements the proxy pattern to provide the right context to our function that executes on a timeout. Click on the bigger button, and this time you'll find that the animation does not run right away. There'll be a gap of 2 seconds, and then the size of the box will be bigger. And you can see that the value of this within the function that is run on a timeout is the right reference. It refers to the target object on which the click event was fired, our button. You can play around with this button as many times as you want. When you click on the bigger button, you'll have to wait for 2 seconds and then the event handler will execute on a timeout of 2 seconds and the box will become bigger. You'll see the exact same behavior when you click on the smaller button. 2 seconds will elapse and then the box will animate to become smaller by 50 pixels in each dimension. We've successfully executed our event handler on a timeout using the proxy pattern. The proxy pattern was implemented using the bind function on a function object. Now that we know what we need to do, set the right context for our event handler to execute on a timeout, let's do this using a slightly different technique. So comment out all of the code that you have now and let's start afresh. I'm going to wire up the click event handler to all of the buttons, that is the two of them that we have on our web page. in exactly the same way as we did earlier. The animation code to make our button bigger and smaller, once again, I'll execute on a timeout. I want this function to execute with the right context. I want it to have the right reference to this. So when I invoke set timeout and specify the function that I want executed, I'll use the $.proxy method in jQuery. $.proxy takes as an input argument the function that we want executed and the right reference to this for the function. That is the context in which we want this function to be executed. And this is a type of proxy pattern as well. We invoke the $.proxy method on jQuery, pass in the function that we want executed, and the second input argument is a reference to this, which within the outer event handler here is the target object on which the click event was fired. And this $.proxy invocation will ensure that our method is invoked with the right context. The rest of the code within this function remains the same. We'll write out to the console log the value of this to ensure that it's the right target object. And once more, we'll check whether the ID attribute for the button is bigger or smaller and correspondingly animate our box to be bigger or smaller by 50 pixels. If the ID is invalid, we'll print out to the console log invalid ID. Let's head over to the Chrome browser and see if our current implementation of the proxy pattern works. Click on the bigger button, and 2 seconds after your click event, your box will become bigger. Its height and width will both be incremented by 50 pixels. Let's switch over to the console logs, and you can see that we have the right value of this within our function that runs on a timeout. That function has the right context thanks to our use of the proxy pattern. We know that our code runs just fine. You can test for this and continue playing around with this page. When you click on a button, there will be a 2 second lag before your animation code executes, but everything will work correctly because we have the right context for the function to execute. In this course, we continued our exploration of common structural patterns in JavaScript. Specifically, we understood and then implemented the flyweight, adapter, composite, and proxy patterns to model structure between the components in our system. In addition, we also covered the implementation details of these patterns, such as the use of the flyweight pattern for event handling on the browser, mitigating inefficient memory usage, and implementing centralized event handling. We used the adapter pattern to offer a consistent interface and thus mitigated the burden of specialized checks. We implemented the composite pattern in jQuery, used the proxy pattern to cache data, and to execute functions with the right context. At this point, you possess the knowledge needed to correctly identify situations that call for the use of the flyweight, adapter, composite, and proxy patterns to model structure between the components in your system, as well as to effectively implement those patterns in JavaScript. You're now set up to move on from structural patterns to exploring behavioral design patterns, such as the observer and iterator patterns in the next course.